Okay, good afternoon, everybody, and welcome to the Construct Innovate webinar series on sustainability planning and construction, which we're running in association with Engineers Ireland. This week, we're going to talk about passive house design. So similar to other weeks, we've got three speakers today. So our first speaker is going to be Helena McAllam, who's going to talk about passive house and lessons learned from design and delivery of buildings. Then we have Stephen O'Shea, who's head of sustainability construction and reporting at Cairn, and he's going to talk about adopting the passive house building standard at scale. And then I'm going to do a talk on performing monitoring of homes. Are we achieving low energy homes? And I've also got Dr. Paul Moore in here, a colleague of mine, who's going to help with some of the Q&A afterwards. So we're going to have the three short talks, and then we'll follow on after those with questions and answers afterwards. So if you have any questions to pose to any of the speakers, please put it in the Q&A box at the bottom of the screen. So not the chat function, but the Q&A box at the bottom of the screen. And we'll bring all those questions together and pose them to the speakers at the very end. So without further ado, I'm going to pass over to our first speaker, over to Helena.
Hi everyone, I'm Helena McAllam. I am an architect based in Galway. Our practice has been involved in the delivery of passive house buildings for about the past 12 years. I am a board member of the Passive House Association of Ireland and I'm chairperson of the RAI Sustainability Task Force. I suppose I've always had a particular interest in how our buildings actually perform, so designing for performance and with a focus on and that particularly, I suppose, initially on the operational energy, and I suppose increasingly so the carbon and the embodied carbon. So looking at the whole life carbon picture or overview of our buildings and how they perform. Design for that high level of performance. So I'll bring you through some of, I suppose, some things we've learned over the last 12 years and how our approach is maybe evolving or the direction of travel we're taking in terms of delivery of our passive house buildings. So first of all, just to run through passive house, when we refer to passive house, when I refer to passive house, there's only one thing that's a passive house for me, and a passive house has is a third party independently verified with a plaque on the door, a passive house building complying with the German passive house standard and certified to do so. I suppose I think it's very important that you actually meet the full requirements of the standard if you're using this kind of terminology around passive house. So we're the Passive House Classic is, I suppose, what we would all be familiar with. So that's based on a 15 kilowatt hour heating demand per meter squared per annum. That's, I suppose, at an air tightness level of 0.6. So that's kind of, I suppose, the classic and what we've been kind of, myself and other architects have been delivering over the last couple of decades in Ireland in terms of passive house building. We've, in recent years, we've seen the introduction of Passive House Plus, which looks at a building with that operational energy performance as the passive classic, but generates sufficient energy to effectively cover its energy demand for that building. Passive House Premium then refers to where we have similar to the previous two, but that it generates more energy than it actually requires in terms of its on-site renewable energy generation. And we're seeing increasing interest in terms of passive certified EnerFit, so passive house certified retrofit. And we're seeing that at the moment, just on the drawing boards over the last couple of years on site presently, EnerFit in the domestic and the one-off retrofit space. We're also seeing it just recently in terms of some office space, almost like Pathfinder type projects, which is kind of very interesting to be involved in those and to be testing those to try and meet that quite onerous requirement of EnerFit, which is the retrofit standard for passive. And I think it's also worth a mention that the Passive House Institute in Germany also have a low energy building standard, which is quite similar to the EnerFit type standard in terms of performance required, but it's a very good low energy house, albeit it doesn't meet the Passive House Classic requirements in terms of air tightness and in terms of heating demand. But I suppose it's still a useful guide and still better than a lot of maybe our building regulation compliance houses, particularly where you're trying to do better in terms of the air tightness of your building. So why passive house? Why do we do it? Well, when I'm talking to clients, it's like we've been, as in it's around the comfort. Yesterday I met clients in relation to a potential EnerFit project and we're talking about the health benefits. There were a certain age, health was a consideration for them. One of them was sick recently. So around comfort and health and air quality in particular. Obviously there's the energy efficiency of the really highly insulated building fabric. And again, being responsible in our consumption of energy linked to that. Future proofing, the houses that we built 12 years ago are meeting what the RIAI would define as targets for 2030 in terms of the operational energy requirement or consumption of those buildings. And that's measured consumption, not what the model says. That's actually recorded consumption on site. They're meeting those metrics. So again, that's from 12 years ago, meeting what the Royal Institute of Architects are guiding as good for residential for 2030. So again, there is that extra layer as designers and architects. We're always as design teams, we're always trying to do our best and deliver the best we can, buildings we can. I suppose the extra layer of the passive house is a whole other layer, quality assurance. There's a yes, no, there's pass fail criteria. You either pass it or you don't, particularly in terms of air tightness or thermal bridging, or the U value requirement, the overall fabric heat loss of the building. So there's it's quite, I suppose, prescriptive in terms of its design, but also its execution on site. And that's kind of why we like it, because it's you can't nearly get there. It's a goal or it's not a goal. So it's which does set a target for the whole of the team, both in terms of the design and in the delivery of the project on site. That's why we value it. I suppose the context of this is all sitting in for us as an office, and I suppose hopefully for other design teams. There's 3 years ago, the REI issued that, I suppose, a design for performance, a set of metrics looking at the kind of operational energy our buildings should have, and we should be designing now to be kind of fit for purpose in 2030. The kind of embodied carbon those buildings should be, the water consumption that we should be designing for, or reducing that water consumption, and then around health and well-being. That's related to overheating and radon and air quality, for example, and then our biodiversity impacts of our buildings. So that's 3 years ago. We see now that the Energy Performance Building Directive early in the year pretty much aligns with some of these definitions in terms of reducing the operation and the demand of our buildings, such that it's feasible to look at renewables on site or close to that site to service that building's energy demand. And again, that also the IGBC, the Irish Green Building Council, have referenced the RII Climate Challenge as in part of their local targets for net zero carbon definitions back in May, which you can find. There's links to this. I'm assuming the presentation can be shared afterwards. So that's the context. When we say passive house buildings, passive house, I suppose, just to bear in mind, it can be applied to almost any building type. So we have Southwest College's Erin Campus up in Enniskillen. We have Enerfit Social Housing in Dublin. We have the Entopia Office Retrofit, Educational Office Retrofit in Cambridge. We have St. Siddle's, a swimming pool in the UK. And then we have another example, Mozart's office building passive certified in Enniscorthy. So again, the energy performance standards and the requirements can be applied to pretty much any building type. My sister's involved in an archive at the minute, the designing of a passive house archive in the UK. So again, there are precedents, particularly in the education space in the UK, passive house, particularly in Scotland. So we're seeing, just to keep in mind, I'm focusing, just the nature of our work is mostly residential, so I'll be focusing more on that today, but to keep in mind that this is, it can be applied to any building type as a design for performance standard. In terms of the process here, so there are a number of modelling tools that we need. The guesstimates are gone, so it has to go into the model. That model has to be reviewed, a quality assurance process by our proposed building certifier before we even think about going to site with this project. So we start in our Design PH, which is a SketchUp plugin to help with modelling the building. It makes it a lot quicker to populate our passive house planning package software, which is that second band, which can be tedious enough, but at least the Design PH can help with some of that. Again, these are inexpensive tools, and very accessible. So with a little bit of training, it doesn't take years of training to be able to execute or to put a model together, but it does take attention to detail. And again, in terms of softwares, it's at the entry level in terms of costs, very accessible from a cost perspective. And then I suppose the other key skill that we need with us is thermal modelling and the ability to check what our thermal bridges are like and assess them in terms of the heat loss associated with those junctions in the building. So the kind of guidance we're using, so we have the passive house planning package. It's manual, which is invaluable, a really important document. And again, when you purchase your PHPP software, you can get that particular manual. I think another thing useful for as a practice or as a design teams using designing buildings to passive house is the RIBA, so Royal Institute of British Architects Passive House Overlay, which sets out almost a pathway in terms of how you might integrate. You know, you may be using a designer that's independent from your own office. Your certifier may well be probably independent as well. So how, I suppose, relative roles and responsibilities are set out, and I suppose a pathway for delivery of passive house buildings in that document, which is very useful reference. We also have the LETI in the UK have some very, to get a, I suppose, a sense of, you know, as designing for performance more generally, their documentation is very useful around the climate emergency design guide. And a lot of the kind of ballpark or the rules of thumbs would pretty much align with passive house and the passive house modeling, you know, as the passive house design that we would use in the office. So again, they have useful rules of thumb to get started, and the operational energy modeling guide as well, another handy document to have nearby if you're venturing or new into this space. Things around design, I'm not going to go to the detail because I kind of need to keep, we have a tendency to run over, so I better hurry up. But again, like we have obviously, you know, we have a lot of our passive house buildings are one-off buildings, and might typically have a beautiful view of the sea or something here over Galway Bay, and we're kind of that challenge of things like managing we have to manage our solar gains, which we need, and in line with passive house principles, with that risk of overheating. So again, the passive house planning package will highlight to us if there's particular issues in terms of design or mitigation needed. So for example, in these buildings, you're looking at integrating of overhangs to help control that, and combined often with maybe some element of reviewing the solar factors to the glazing to reduce overheating risk where you have a particularly large window and you need to try and manage that. In an ideal world, you would have a smaller window that's on the right-hand side, but when a client has a fabulous view, it's a little bit hard sometimes, and it is a source of debate on projects, whether we can actually reduce the scale of some windows, which sometimes we'll bring out the passive house planning package modelling to kind of explain why we would be keen to reduce things or adjust the design, you know, that there might be some compromise needed in terms of balancing reducing overheating risk and balancing obviously what's the client's desires around a particular view or a particular window of a certain scale. So there's quite a bit of debate on some projects around those things. Other design considerations around how do we deal with our thermal bridges? Can we put a system like on the left-hand side, we have core insulated raft foundation system. And again, that can really, this is a timber frame building. So again, our thermal bridging and our assessment of that is so much easier. And all of those heat losses, or the vast majority of them, have been designed out in that approach. We have then in the more traditional, this is a single leaf block with external insulation. Again, the courses of those Quinn blocks at the bottom, as you can see coming off our raft foundation in that instance, pretty carbon intensive in construction, but also a lot of modelling required around those junctions to ensure that the thermal bridge is properly assessed and within, you know, suitable for the passive house building that we're trying to deliver, and assessed in terms of its thermal and condensation risk. And then the other thing, the image on this was sometimes we like as architects to make things as challenging as possible for some of our design team and construction colleagues. And again, in this instance, a portion of exposed ceiling in a passive house, and then you're combining trying to manage air tightness at those junctions where, you know, so there's a lot of thinking and strategy and forward planning needed. And I suppose sometimes we could be trying to make that a little bit easier for our design team and construction team colleagues. So I'll just very, very quickly look at, I suppose we've been building, initially we built in cavity wall construction with a wide cavity here in the West. The West in particular seems very attached to their cavity walls. We've built buildings with external insulation. So again, we have our EPS insulation, typically EPS insulation to the outside of our block and flat type construction. And then we have a very robust timber frame construction. So we have a very wide stud with, we're using a system at the moment with long lead structures, and then we're using that in a number of projects where we have a timber frame system filled with cellulose and combined with wood fibre and sheep's wool insulation to the surface cavity. So again, so I suppose we have been delivering passive houses in all of these forms of construction. There are considerations. There is a complexity to the cavity wall construction, particularly in relation to you know, how we manage the thermal bridge around the window opening and the air tightness details, for example. So there's a complexity there, which, well, to be honest, we've managed to get through it, but it's taken a couple of iterations to get to a point where we find that kind of relatively easy to deal with. Again, there are increasing numbers of products which make this easier, but as we started out, there was a lot of those weren't available. We have the block and flat of the external, the benefit of obviously the external insulation makes it a great deal easier to deal with the thermal bridge element around the window, and the air tightness, because we're relying on a wet plaster, but a lot less complexity to this example detail. And then with the timber frame construction, we're looking at where we have an element of it's almost a combination of an external wood fibre board to the outside of that system. So again, we have, you know, nearly the benefits of both the previous systems, as in we have that external insulation combined with the insulation in the main stud line. So again, our membranes are doing the work here, and that's about, I suppose, care and attention to detail by the subcontractors and the teams on site. All three of these rely really heavily on skills and attention to detail on site. To call a spade, the air tightness is a really tricky bit. And I suppose we're kind of, if we look at, we've taken some of our passive house buildings of different forms of construction and had a look. These are, I think most of them are certified at this stage, with one or two in the process of certification. So you can see the different construction types, a lot of masonry, but you can see the ones that have performed better are typically the timber frame and the external wall. They're not the standard masonry cavity construction. So you can see there's a little bit of, and we're noticing that in some of our other projects as well that are at a very preliminary stage in terms of their air tightness on site presently. So very much from our own practices direction, we're definitely leaning towards the delivery of more timber frame passive houses, and both from a whole life carbon impact and also the ability to, you know, meet that air tightness standard on a kind of wet, sometimes windy site in the middle of Connemara or on the edge of Galway city somewhere. So I suppose that's kind of, you know, it's proving easier to deliver with that form of construction presently. Just to note, you know, a number of those houses that I would have listed, we have been monitoring and checking with our client. If we're not monitoring, we're checking in with them about once a year to see what their consumption is like. And the vast majority of them are coming in under 35 kilowatt hours per meter squared per year. That's for all of their energy consumption and without taking the renewables into account. So that's the kettle and the oven and the home computer, plus the heating and the hot water in those houses. They're typically in the 20s, to be honest, between 23 to about low 30s. So that gives, I suppose, it's why in terms of the kind of buildings that we do, where I suppose passive houses allowing us to build the buildings we think we need, and we know we need between now and 2030, because these kind of numbers are manageable in terms of when you have a whole consumption of a house at these numbers, the use of PV or renewables on site becomes very feasible to actually cover the energy consumption of these buildings. So I suppose we're still learning more and monitoring the performance of our buildings. I suppose we're noting that design team skills and tools we've been learning over the last 12 years and refining how we're approaching it and to try and make it easier to deliver, designing to make it easier to deliver and achieve the requirements on site. The construction team skill and training, again, was speaking to an air tightness contractor a product supplier in Ireland last week, and they have trained 1,500 people in the last 12 months in relation to air tightness. So that shows, just shows a willingness and a capacity there that, you know, as in to try, and the hardest bit of this is that stringent air tightness requirement, but it's great to see that many people engaging in that training. I suppose we've been delivering it in various forms, and I've shown you the three key ones that we've been using in terms of forms of construction. To be straight, some of them are easier than others to deliver, or a little bit easier for your contracting team to deliver, but it is deliverable in most of the main forms of construction. And that's what we've learned. So you might just sign off there if that's okay, Jamie.
Brilliant. Thanks, Helena. That's very good. So, so as well as giving us an introduction to passive house and the standards trying to achieve, to actually see it in action, and that it's not just one form of construction that you need to stick to achieve passive house standard. You have lots of options to you, but it's around, you know, your detailing and then delivery on site, and that's whole supply chain to be able to work together to deliver the quality construction that you need. Okay, so now we're going to step over to Stephen O'Shea from Cairn. So he's obviously delivering at scale. It's one of the largest house builders in Ireland in there, and how they're adopting passive house building standards at scale, or why would you do this? Yeah, so over to you, Stephen.
Thanks, Jamie, for the invitation to speak. And I suppose I'm presenting a very different perspective on passive house to what Helena has just been talking about. We released 2 weeks ago, I think, our position paper, which goes into, really what I'm going to discuss today in a bit more depth. It's really setting out our reasoning behind, why we see passive house as being important for us and for the wider industry. This is it. This is our why. It's the question that everybody asks is, why the hell is a company the size and scale of Cairn, with as complex a supply chain as we have, and as large an operation as we have, why do we see passive house as being the way forward for us? So what I've done here is I've pulled out a few quotes from our position paper. Really, these are the headlines. I'm not going to keep you long. I've given the QR code there, and it'll come up again at the end of my talk. You can link to the position paper and download it there. But really, look, here we go. We're straight into it. This is it in a nutshell. We believe that we need to be able to build in a sustainable fashion at scale. We're in the middle of a housing crisis and a climate crisis at the moment. We need to be able to respond to both simultaneously, and it's about finding methodologies and systems for doing that. We need lots and lots of homes. We need them to be well connected in terms of public transport and local amenities. We need to build them as efficiently as possible, and ideally they will be as efficient to run as possible. Helena has showed beautiful examples of one-off passive houses on their own sites, and that I suppose is an aspiration that most of us would have. To have a property like that, but it's not going to be within reach of the majority of the market. So what do we do for those people? I'll talk a bit in a minute about our decarbonisation targets as a PLC, but really when we started to look into the passive house standard, and trying to make it fit to our operations and the way that we work. Really what we found is that while it does take extra care and attention, and there is a level of detail involved at design stage, which maybe wouldn't be the norm when you're building at this kind of scale. At its heart, passive house is very simple. It's definitely repeatable, and it's applicable to any building at any scale. So for a company like Cairn, we believe in finding the most efficient ways to build quality buildings, and refine and repeat those processes over and over again until we get better at them and we get more efficient at doing them, and our delivery gets better. It's a standard that really rewards care and attention, and it does get easier with repetition, or at least we really hope it gets easier with repetition. We haven't started into this in a small way. That's a shot from our first passive house scheme in Piper Square in Charlestown. And it's going to be 590 certified passive house units by the time it's completed. That shot is probably 3 weeks out of date at this point. There's at least another floor, if not two, on that block in front. That you can see there in the shot at this stage. So, taking it all back to Professor Wolfgang Feist. you know, he was struck by the fact that builders or construction professionals were changing the way that they worked, or at least changing the materials that they were using. But the results weren't, they weren't getting the results that they expected out of the new materials or the new ways of working. And that's what inspired him to find out what was being done wrong and what was needed to put it right. And in Cairn, our mantra in terms of Passive House is that we're using the same ingredients and we're just putting them together in a different recipe. So we've always been building well-insulated houses. We've always been paying attention to air tightness, even though, this is now pushing us to new levels. Ditto with thermal bridging. We've always been paying attention to our thermal bridging. We've always assessed the FRSI values for all of our thermal bridge junctions. Now we're pushing those efforts a bit further. So when you think back to when Dr. Feist was setting up the Passive House standard in the 1980s, it was a very, very different landscape. So when he was talking about air tightness, people, well, certainly Irish people, would have thought that he was a bit mad. Sure, fresh air is great for you. Why would you want to make your building airtight? When he's talking about thermal bridging, I, for one, had no idea at the time really what that was about. And then when he was talking about quality control and testing and certification and those elements of the Passive House standard, it probably sounded a bit Big Brother. It sounded expensive and it sounded slow. That certainly if you were intent on working at the pace at which a company like Cairn works at nowadays, the last thing you wanted was to have, call a halt to construction to carry out an airtightness test, in mid-flight or something like that. But fast forward to 2024, we've had, coming on to 10 years of the BCAR regime in the country. We've had our building regulation standards changed, is it 3 or 4 times since the Passive House standard came out. We're all getting more familiar with these concepts, or we all are more familiar with these concepts. So the gap between what business as usual is and the Passive House standard is narrowing all the time. So then you might ask, why then do we want to embrace what is now quite an old standard? It's about 30 years old at this point. And for a PLC like Cairn is, really all that comes down, at least the starting point for that would have been the performance gap. So we have science-based targets for decarbonisation, and we have committed to reducing there are scopes 1, 2, and 3 in carbon, and please excuse me if you've heard this a million times over, but scope 1 and 2, if you like, encompasses our own operations and the energy bills that we pay. Scope 3 then is about the upstream portion of our value chain and the downstream portion of our value chain. So upstream is everything to do with the materials and the suppliers and the subcontractors that we employ on our sites. And then downstream is our customers and how they use the houses and or the homes. And one of the parts of our scope 3 carbon footprint is the energy required to heat and light and make hot water in the homes that we build for a period of 60 years after we hand over the keys. So when we measured our carbon footprint, what we find is that something like 50% of Cairn's total carbon footprint in any one year is tied up in the operational energy for of the houses that we are building. So that's a big number. And when we looked into how to get it to come down, we realized that we were making, we had to make a big allowance for the performance gap. And that's the gap between what the BER cert says is going to be the energy performance of the building versus what what the actual energy bills of the people living in that building is going to say that consumption is. And we knew from research, lots of research, that the passive house buildings basically perform to their designed performance. And Helena just gave another piece of evidence to that, which was the 35 kilowatt hours per meter squared per year measured energy performance across all of the buildings she was talking about, encompassing all of the energy sources, heating, lighting, hot water, and plug loads, which is, that's obviously the really tricky one to try and predict. So despite the fact that we were using good ingredients and we were inspecting and monitoring our operations on site, because we were building to what turns out to be a fairly flawed standard in terms of the Irish building regulations, we're not getting the if you like the reward for that. Whereas by taking a relatively modest step up in our own performance and our own operations, we're then able to slash that that part of our carbon footprint. So this quote really, the reason I have this in here, we've been really heartened by the reaction both of our own employees and that of our supply chain when it's come to rising to this challenge. Change is always tricky. Nobody really enjoys it. This is, it's a new way of working. It's somehow calling into question everything that you've ever done before. There's a new level of supervision. There is a new certifier in the process. It's entirely voluntary. Nobody is putting a gun to our heads and telling us we have to do this. So, understandably, people wanted to know, well, why the hell are we doing this? But actually, once we've explained this is the why we're doing it, the attitudes have been really positive towards it, and everybody is embracing the challenge. They're having to learn this new recipe really, really quickly. We haven't started out small scale. We haven't done any, a couple of units as a pilot project. We've aimed very, very high, and everybody is rising to the challenge. And we hope that, when we get through the pain of these first few projects, that, people will feel justifiably proud of what they've done. To take another quote from Jeff Colley, all of our supply chain, all of our, our own operation staff will be responsible for delivering what are, truly world-class buildings here in Ireland. So second part, if you like, of the why question is, it's one that our CEO is extremely strong on. To him, carbon targets and so on and so forth, yeah, they're fine, but they're a little bit, I don't know, they're a little bit academic, or they're a little bit businessy. Whereas what he's much more interested in is what the impact is going to be on our customers. Why are we making life hard for ourselves? Why are we being so ambitious? This is why. It's about or at least this is also why. It's about the impact on the lives of our customers. This image is from Goldsmith Street, which was the first social housing scheme and the first passive house scheme to win the prestigious Sterling Prize in the UK. And it's the word "actually" in that quote that really stops me. There's a sort of, I don't know, I think you can hear a sort of an amazement in that they've actually saved for things. And that's how life-changing that the experience of living in a passive house can be. And again, that it gives us a much better reason, to be honest, to take on this challenge, when we understand what the downstream impacts of all of the efforts that go in on site to achieving a really challenging air tightness standard. What the impacts of that actually are. This is not a theoretical exercise. It's not numbers on a spreadsheet. It's not even numbers in our annual sustainability report where we talk about tons of carbon. It's about changing people's lives at the end of the day. Another kind of feature or another point about the way that we've chosen to do this is that our all of our schemes that are on site at the moment. So what you're looking at here is somewhere north of 1,750 passive house apartment units. All of them will be going to, they're all part of mixed tenure schemes. So it's a mixture of social, affordable, cost rental, etc. This isn't high end, the high end of the market. These aren't exclusive developments. These are going to people for whom the fuel poverty is a very real prospect, and to whom the savings are going to be especially welcome. And again, that's part of that feeds into the pride that people are feeling here in Cairn, and it's really why we release this position paper. Is we want everybody within the industry to embrace this way of thinking, and to start really designing and constructing for performance. There's an expression I heard recently, that business moves faster than legislation. I don't believe we can wait for building regulations standards to change in order to catch up. I don't think we should do that. I think we should be, more people than us should be saying, no, we're going to go further because we can see the benefits in this. And sorry, the second part of that quote is, business moves faster than legislation, but science moves faster than business. The world isn't waiting for us to get our legislation right. We all need to be taking action now. It couldn't be any more urgent. Thank you.
Brilliant, Stephen. Thanks a lot. Thanks for the presentation, but also thanks to Karen as well for taking a leadership role in this. I mean, building at scale and showing that this is possible, but showing that it's not just for people that can afford it. That passive house should be for everybody in there, and hopefully that lots of others take inspiration from that leadership role and it becomes the standard for all. So I'm just going to talk a little bit about monitoring of homes, but there's no case studies here on passive house homes, but to show really why we need to, why we should be monitoring and around performance. So just go back to basics. We have, the building energy ratings in there. So we use what's called the dwelling energy assessment procedure to get our building energy rating for our homes. That effectively calculates the energy performance and associated carbon dioxide emissions for heating our homes, for the hot water, ventilation and lighting in there. And then for non-domestic buildings, then it's NEAP that we use, the non-domestic energy assessment procedure that creates the BER. So these are what we use in Ireland for compliance. So to show that we're compliant with Part 10 of the building regulations. So they're not performance-based tools. What they have in them, they have basically standardized operation conditions. There's standard assumptions underneath them. And then from it, it'll give a calculated expected annual energy consumption, associated CO2 emissions, like on the right-hand side there, and obviously associated rating with them. So they're really asset energy rating rather than operation or measured rating. And one of the issues is like that, our building regulations is the minimum standard that we have to build to. Okay, they're not the gold standard. It's not it's not in a something that we're trying to achieve to say like, this is, look how well we've done. This is actually the absolute minimum standard. And if we're designing just according to using the building energy rating and DEEP as a design tool to achieve the highest building energy rating at the lowest cost, then we don't necessarily deliver the best performing home for people, or best performing building for people. So that's why using the likes of the PHPP, which is the software package for passive house design, means that we move towards more of a performance-based design. So if we take this study that was done in the UK, where they have 50 low energy non-residential buildings, and what they find, and you see the graph there is showing the ratio of the actual CO2 emissions associated with operating the building compared to the estimates of the calculated values, the measure compared to the calculated value from the VER estimates. So we can see that, you know, it could be up to 10 times as much as amount of emissions associated with operation of the building as what the BER would suggest, and very few of them are actually less than 1. In other words, very few of the BERs have underestimated the associated CO2 with operating these buildings. So these are non-residential buildings in there. And you can see the performance gap is averaging 3.5 times in terms of the building energy rating. But that's just the energy associated with operating our buildings, mainly for the space heating, the water heating, the lighting, and so on. But, you know, our primary interest in our buildings is the comfort or well-being. So we're in buildings more than 85% of the time. So the primary thing is to have our buildings that they're comfortable and healthy homes to live in. So when we talk about performance, we don't want to just consider performance in terms of the energy consumption or the associated carbon emissions associated with that. We also need to think about the thermal comfort conditions inside, temperature conditions, the relative humidity, a combination of temperature and relative humidity, so we don't have issues with mold or so on in there. The air quality, so to make sure we get enough fresh air into our buildings in there, so we could use CO2 to measure that, and the health of our occupants. So we'll have talks in a couple of weeks' time around VOCs and other things in terms of the indoor air quality. So within DEEP, which is what, as I said, it's a standard assessment tool to get the BER and the building energy rating. The default in the BER for the living room is at 21 degrees Celsius. But if we look at this study here, where we've monitored a number of homes, in there we can see we monitored them on the left is before they were retrofitted, and the right is after they were retrofitted. We can see that the range of temperatures, average temperatures over across the day. So we have from midnight to midnight effectively. We see the range of temperatures in the living room in these different homes on average over the measurement period in there. And pre-retrofit, you can see that predominantly it's less than 21 degrees, but it varies. And then post-retrofit, it's less than 21 degrees, with some of them up around 21 degrees. So that's the actual condition. And then the bedrooms, the default in the BER is that it's 18 degrees Celsius. Or actually what we've seen here, both pre and post-retrofit in those same homes, and that the bedrooms are typically in a similar temperature range to the rest of the house in there. So the underlying assumption that within the DEEP software, the bedrooms are 18 degrees Celsius is not representative now of how we heat our homes. So maybe in the past, when we had mainly an open fire or a stove or something in our living rooms, so a single heat source for our living rooms, and then maybe a different heat source for the rest of the building, maybe. But now, because we have, you know, we have a lot of central heating systems, and the way people have set their homes in there, that the setting of the temperature, the default setting for the temperature it seems to be above 18 degrees Celsius. If we look at what the impact of that is, if we have different temperatures, so here we have 8 homes that have heat pumps in them, and the dots there are the temperature. So the theoretical temperature in there from DEEP in the yellow, and then the grey, which are the ones higher up, is the actual measured temperature for each of those homes, average measured temperature for each of the homes. And you can see then that the energy demand, the blue is the measured energy demand, the orange is the theoretical energy demand, and you can see that the measured energy demand can be significantly higher than the theoretical energy demand. And effectively, the main thing that's driving that is that the set points, or the set point temperatures within the rooms are much higher than what the theoretical value would be. So obviously that's going to have an impact in terms of your energy consumption and the cost to run your building. But factors that contribute to underperformance of heat pumps are lots of things. So one of them being the set point temperature within it, or the requirements for the heat pump. Another thing is the sizing of the heat pumps. If we don't size up the heat pumps correctly, we can end up that they're working much harder than they need to, and therefore are not as efficient as it could be. The temperature difference between the indoor and outdoor environments affects the heat pumps in there. So we have a different performance in wintertime than we have in summertime, for example. So that little graph on the top right is the coefficient of performance, effectively the energy supply from the heat pump divided by the energy consumed by the heat pump. And you can see if the temperature difference, so down the bottom is the temperature difference, which is the temperature difference between indoor and outdoor. If there's not a big temperature difference, we can get a much higher coefficient of performance, maybe up to 6 or 7, whereas the temperature differential reduces down, you get a reduction in coefficient of performance. Occupant behavior, how we use our buildings in there. So typically heat pumps provide both space heating, but also hot water as well. So how much hot water do we need? How long we take the showers, the baths, so on in there will affect how the heat pump operates, because it has to cycle through creating hot water and also space heating as well. But also how we ventilate our buildings, how do we leave our windows and doors open, and so on in there. So lots of different ways we use our buildings. And then the installation of the heat pump. So this is a picture that we took here in Galway, for example, where the heat pump is very close to the wall, so there's not enough circulation for airspace for air to get around the heat pump. So it's not going to perform as optimum as it could do because of how poorly it's installed. So I'm going to look at some I suppose, standard ways we measure these buildings to see how they perform. So this is the whole dwelling heat loss. So we want to look at both the fabric and the background ventilation. So effectively heat loss through the fabric in there. And also through background ventilation, like for example, air gaps around the place. So we have, so you have to do this. So what we can do is we can work it out from the heat loss coefficient from deep. So within the calculated method, we can work out what the heat loss coefficient is. And we've done that for 5 houses here in the table on the right-hand side. We can measure it. So we can measure it using a coheating test in there. We basically put a heat source into the building, leave it running for a couple of weeks at 25 degrees Celsius. And then what we can do is work out the temperature in minus temperature out, and how much consumption is taken to keep that temperature 25 degrees Celsius. And we'll plot those on the graph here. And then from that, then the gradient or the slope of that line will give us the heat loss coefficient in watts per Kelvin. And we might have a designed heat loss coefficient that might have been a lot lower than what we have measured. But actually in these 5 houses, they did quite well in terms of what was calculated using deep. The values are pretty close across, except one of them is significantly different in there. Then from the heat loss coefficient, you can work out what the heat loss indicator is, and effectively for your building to be heat pump ready, it should be less than 2. The heat loss index should be less than 2. So most of these buildings actually meet that requirement. Some of the heat pumps that you can buy off the market, standard heat pumps, you can actually get data straight out of those, and they have an SD card inbuilt into them. So for example, you can get the electricity consumed, you can get the delivered heat, you can get the room temperature, you can get the outdoor temperature in there from the temperature sensor that's down here. You get the flow and return temperature, flow rate, and so on in there. So we look at 2 quick case studies here that we monitored that are retrofitted buildings. They're basically semi-detached houses. They got new external doors, cavity insulation, roof insulation, new PV, and an air-to-water heat pump in there. And the other one was pretty similar, except they had external wall insulation in there rather than cavity wall insulation. The first house was actually unoccupied for most of the measure period, whereas the second house was occupied. Now, I'm not going to spend time on these because it will take a little bit of time, but effectively what we can see here is in this graph from the data from the heat pump, we can see what length of time it is spending on each mode. So the pink is that it's turned off, then the purple is space heating, then the next one to that is Legionella mode in there, so we have to heat it up to make sure we have no Legionella problems. Then you have domestic hot water, it's light blue, and you have freezing in there, which is a dark blue in there. So the heat pump goes through a freezing cycle when it drops below a certain degrees outside in there to make sure that it doesn't freeze up. And then underneath here, we can see the temperature. So the average temperature, we can see the maximum, minimum temperature, we can see the coefficient of variation in terms of temperature in there. But effectively what ends up happening in this one, you can see this is working pretty hard in December and November. It's nearly all on in terms of the space heating, because the set point temperature is at 19 degrees and it's working really hard to achieve that. Whereas in the other house that was occupied, in there, the occupants of the house decided to turn down the set point temperature and ended up saving a significant amount of electricity consumption then by going down to 18 degrees Celsius in there and using a lot less electricity in there. And this dark blue one here is the hot water consumption. So you can see that clearly from here, where high electricity consumption And heat delivered here on this one compared to the other one over there is a lower heat delivered. So there's lots of things we can measure. We put sensors into our buildings to measure these and understand them. So for example, this is a set of homes that we measured here in Galway. Basically, we want the temperature to be somewhere between 18 and 24 degrees Celsius to be in the comfort range. We can see one house here is significantly below the comfort range, with a small proportion in the comfort range and a little bit where there's overheating here. So the red is overheating in there. We also want those same homes to be within a humidity range of 40 to 60% relative humidity. And again, we can see that some of them are a bit dry at some times of the year, and some of them are above the range. Now, above the range is going to be more problematic than below the range here. We also want to make sure that there's good air quality, in other words, adequate ventilation, that the ppm rate in terms of CO2 is less than 1,000. And again, we can see most of these houses perform well relative to that. We can look at the data across hours of the day. This is average across hours of the day for temperature, relative humidity, CO2, and so on. So we can see if there's issues at certain points of the day in terms of performance. We also can take, say, a given room within a building, and we can look at this temperature for that room, and we can actually give it a rating. So a rating, for example, is performing well because there's a lot of green here. We're within the temperature band of 18 to 24 degrees a lot of the time, but sometimes here it's well outside. And now this would have been an unoccupied house at that stage, but you can see this house as well has issues with overheating during some of the summer months. Relative humidity, again, we can see that there may be issues with high relative humidity during some of the months here, where it's red, where it's above 60%, and it can be quite dry at sometimes as well. And then CO2 as well for this given home across the year, across these 9 months. That sometimes here there's some issues in terms of that it's not being adequately ventilation because the CO2 is going up too high. So there's an issue in terms of indoor air quality there. We can use time of wetness, so that's defined as a ratio between the wet periods, so when the relative humidity is above 80% and the total time considered, and effectively mold growth is observed to start for a time of wetness equal to 0.17, and it increases significantly when the time of wetness is greater than 0.5. So in these homes here, for example, the time of wetness doesn't indicate a substantial problem with potential mold growth. There's other ways we can look at it as well. So here we've plotted relative humidity versus temperature. We really want to be in this green zone in here where we're between sort of 18 and, but in here the dark green, ideally 18 and 23 degrees Celsius, and the relative humidity is somewhere between 40 and 60%, or at least between 30 and 70% in there. So that's where we want to be. We really don't want to be up here in the grey zone. The grey zone here, you have a high probability of mold in there. Most fungal growth in this kind of zone here, the H zone, and a wide range for growth in here. So basically, once your relative humidity goes above 70%, but when your temperature then in particular is in here between 20 and 25 degrees, you're going to get significant chance that you're going to get mold growth within your houses. And again, we have the data flowing out of these buildings that we can see the data here. It doesn't take much to shift into the zone here, into this zone here, just increase the relative humidity, keep the temperature nice and comfortable, and then you're into ideal zone for mold growth in there. And you can just see some of the data here from some of the different houses that we're continuously monitoring to see where their issues might be. So you can bring all this in together. This is just an example dashboard here where we look at the indoor temperature, relative humidity, indoor CO2. In there, we're actually measuring those numerically. We can look at the outdoor values. We can look at social indicators like mold, temperature, relative humidity. We can look at satisfaction surveys in there. We can also look at economic things like return on investment, change in asset value, the building energy rating, and so on. But it's a way that we can actually do performance monitoring of our buildings to see how well they perform. So that's my kind of quick run through of just some of the measurements and how we can measure performance of building. There'll be a lot more detail around monitoring buildings in the webinar in 2 weeks' time. With that, I'm going to close the webinar. I'm going to thank our speakers. Like, fantastic to have Helena, who not only in her own practice but also driving this to the Passive House Association of Ireland, but also through her roles within the RIAI as well, for the Royal Institute of Architects of Ireland, and that. So fantastic to have a champion and so much knowledge, and then Stephen as another champion of this, and showing how this why they want to do it at scale, and There's no question of the how, because it's been done, and then we'll see, you know, over the years the performance and it coming in more and more mainstream. So that's fantastic.